Hello ladies and gentlemen, my name is Hartwig Künzel and I'm head of the Hygrothermics department at the Fraunhofer Institute for Building Physics in Germany. For over 30 years we are doing research on the durability of building materials. In this video we will have a closer look at the durability of the stay-in-place formwork system and how it is used in LUCKNOW. In this system, the outermost layer of the structure is made of PVC. This is very prone to solar radiation. Therefore, in the first half of this presentation, we will take a closer look at how we can assess the effects of solar radiation on building materials. In the second half, we will look specifically at your lighthouse project in LUCKNOW. We will have a first analysis of the durability of the construction under the climate conditions there. Let's start. PVC is often used outdoors where it is exposed to solar radiation, for example, as profiles for windows. Here it is very important to determine the effects of solar radiation, heat, moisture and other climatic stresses on the color and other properties of plastics. In Europe, outdoor exposure to solar radiation is regulated by the standard ISO 877. Typically, the following tests have to be performed to assess the durability of PVC parts: notch impact strength, weather fastness and weather resistance, thermal stability and fire behavior. In addition, further tests are often carried out to check the aging behavior of PVC materials, and here two methods are usually used. One method is outdoor tests in which the materials are exposed to actual weathering, and the other is laboratory tests where aging processes can be artificially accelerated. We will now discuss these two options in more detail. Here you can see how we carry out tests in our free field test site on multiple facade elements, for example, on plastic elements as well as other elements. The samples are usually exposed to the weather for several years. This is particularly demanding for materials at the Institute's location in southern Germany. In addition to the heat and moisture factors, which are recorded across the cross-section of the component, the visually material changes are also examined. The first discolorations can already be seen in plastic elements, and these are expected to intensify over the next few years. However, it is often necessary to determine more rapidly the effects of radiation, heat and moisture on the physical, chemical and optical properties of plastics with artificial accelerated weathering or artificially accelerated irradiation exposures that use specific laboratory light sources. Here you can see a large-scale sun simulator that we use in our institute to evaluate the effect of solar radiation on materials for large specimens up to 8 square meters. We can test facade or roof elements and can therefore change the angle of the sun simulator from 0 to 90 degrees. Exposures in laboratories with devices like this are conducted under more controlled conditions than found in natural environments and are intended to accelerate eventual polymer degradation and product failures. It enables the reproduction of almost all occurring radiation loads on components in their original size and installation position. Let's now move to our lighthouse project in LUCKNOW. Here on the right hand side you can see what the stay-in-place formwork system looks like, which is used in LUCKNOW. Here you can see the PVC forms that are set up and then filled with concrete. What conditions does the structure have to withstand permanently? As we can see in the diagram on the bottom left, there are a lot of sunshine hours in LUCKNOW and the UV radiation is very high throughout the year, stressing the material. Therefore, for such a construction, it must be ensured in advance that the material can handle the stress permanently. In addition to the stress caused by solar radiation, it is also worth taking a closer look at the moisture processes that take place in this construction. For this purpose, we performed calculations using the software for hydrothermal component simulation. In doing so, we specifically mapped the construction structure as a digital twin as it is currently executed in LUCKNOW and used the realistic climatic conditions as framework conditions. We calculated two different variants. First, the case in which the construction is built without any leakage. This means that the PVC layer is completely impermeable to water. Neither moisture from the concrete can dry out to the outside, nor can water from precipitation get into the construction. Secondly, we have calculated the more realistic case, which means a construction with the same structure in which the PVC layer has some leakages through which moisture exchange can take place. Now let's take a look at the results of our calculation together. We have calculated for both versions how the heat and moisture in the construction will behave over the next 40 years. On the left-hand side, you see the version without leaks, on the right with leaks. If we start the animation now, we can see how the heat and moisture will behave over the 40 years. On the left, we have the exterior of the construction with the PVC layer on the outside. In the middle, we see our 12 centimeter thick concrete layer, and then inside again a PVC layer. On the top, we get the temperature over the construction. We will not take a closer look at this here for the time being. We focus on the moisture profile in the component structure, as we see it here below. The green line or the green area gives us the information about the relative humidity in the component. When concrete is placed and it's naturally very wet. Here we can see how this concrete continuously dries out over many years until eventually an equilibrium is reached at something above 60%. The blue line gives us the absolute water content. This decreases according to the relative humidity. Normally, concrete dries out much faster, and the equilibrium moisture content is reached after about, let's say, 5 to 10 years. Here the drying process is significantly slowed down by the dense PVC layer. Let's look at the construction again, but let us assume some leaks in the PVC, so which on the one hand rain can penetrate and at the same time the moisture can dry out from the concrete. we focus again on the moisture conditions that we see at the bottom right. Compared to the dense structure, the relative humidity settles at around 80% RH, and the absolute water content also remains relatively high over the long term. This is probably due to the fact that moisture can continuously penetrate the structure from the outside. What conclusions can we now draw from the calculations? On the right, you can see an overview of the calculation results for the two designs. For both variants, it takes about 37 years for the moisture content in the component to level out evenly. Below, we see the moisture content that has settled after these 37 years. As we have already seen in the animation, this is significantly higher in the case of the leaky variant at around 95 kg per cubic meter. In the third line, we see the respective heat conduction of the concrete. Firstly, the value when the concrete is fully dried. Secondly, the value that results depending on the actual moisture in the component. This is clearly worse, especially in the second variant, where the moisture content is permanently higher due to the leaks. Due to the PVC layer, even if a substantial amount of permanent moisture stays in the material, there will be no moisture issues, as concrete is very insensitive to moisture. However, this permanent moisture of the concrete has the effect of increasing the thermal conductivity of the concrete and thus reducing the insulation value, as we are seeing in row 3 of the table. The more additional moisture enters the component from the outside, the poorer the insulation value. So care should be taken to ensure that there are no inaccuracies in the outer shell. I thank you for listening and hopefully see you next time when we talk about durability in the Lighthouse project in indoor.